Well, hello, good morning, and thank you for joining me in my shop. Today is September 2nd, a day here that started out with rain and cloud, but apparently sun is coming. And then in a day or two, very hot weather is going to move in here for quite a while, apparently, like a week or two of hot weather. So, quite a change coming. Okay, now, what to do next with this radio that might be interesting and revealing. With the radio working fairly well, it's kind of going to be hard to find something to change in here that's going to have some dramatic effect on it. The next capacitor I think I want to go after would be called, or could be called, the AVC capacitor. And this capacitor usually resides beyond a very large resistor in the AVC circuit. And I'll explain that in a minute. We'll look at the schematic and I'll explain what I'm talking about. Beyond this very large resistor, and in this radio it's a whopper of a value of resistor. I think it's 11 megohms or something. It's very high. The circuit can be considered to be a very high impedance circuit. In fact, it's almost nothing more than a piece of wire running around inside the radio. Yeah, it's connected to some grids, but it's not really going anywhere. There's nowhere for current to flow along this circuit. That's on the far side of this very large resistor. What that means is a very small change in charge can result in a large change in the voltage or the pressure of that circuit. It's very sensitive to charge coming into it because it's very high impedance. Almost an open wire, as I said. So there's a capacitor in there which is designed or intended to primarily buffer the variations in this AVC voltage that's going to develop on the far side of the resistor. It's not really going to develop there. It's going to be placed there from the other side of that very large resistor. Again, I'll explain this when I look at the schematic. So what happens if that AVC capacitor is a little bit leaky? Well, it's hooked up between the AVC line. I'm pointing at nothing here, by the way, with this stick. It's hooked up between the AVC line at the grids of the tubes, or near the grids of the tubes that are going to be affected by the AVC, and the other side is hooked up to B minus. If that capacitor is a little bit leaky, it can bleed down the charge fairly easily in this circuit, and the result is your bias voltage will not be where it should be. It's going to be less than what it should be. These tubes are biased with a negative voltage. Where do you get a negative voltage in a radio like this? The easiest place to get it is to derive it from the AVC and or from the IF. So the output of the IF, which is 455 kilohertz, gets rectified. The resulting DC voltage could be thrown away. It's of no interest, except guess what? If you turn the diodes the right way, you get a negative voltage. You throw a capacitor in, a couple capacitors in, you can change that from a pulsing RF rectified voltage to a nice smooth DC voltage. And you can use that negative voltage to operate the grids, and isn't it handy when that negative voltage goes up because the output of the IF has gone up, then the negative bias increases and the tube's gain is reduced. So it's just a happy coincidence that all this can be done in such a simple way and so handily in these radios. And that's why all these radios utilize this automatic volume control. What's the real purpose of the automatic volume control? To stop the radio from screaming in between stations. So if you, and I'll take that back. I got it completely backwards there. Forget what I just said. Let's just start again. So why even have an AVC in a radio? Because you could be tuning in different stations of different strengths. So you can have a nearby station. Oh, there goes my coffee indicator. Coffee break time. When you, this is a terrible explanation. Let's go look at the schematic and then I'll be able to explain this better instead of talking to a stick. Okay, now we're looking at the schematic here. So this voltage I'm talking about is developed right here by this tube and these diodes right here. And this is the output of the IF. This transformer is the last stage of the IF. It's coming through here. So at this point, we've got 455 kilohertz, and you shove it through these diodes, and you can build up a DC voltage here. And if if the diodes are turned the right way, you can get a negative voltage building up here. Now, which you could throw away or ignore or just pay no attention to it. But as it turns out, there's a trick that can be played with this voltage. So here it's sent, well, it's sent in two directions, isn't it? It's going this way through this volume control, which is probably 500,000 ohms, something like that. You can go this way, it goes through an 11 megohm resistor. Now on the other side here, there's no real current path. If you follow the wire and you imagine the DC path, you can see how it would get all the way to the grid. And the grid, of course, is just a wire sticking inside this tube. It's not connected to anything inside, so it's going nowhere. The circuit going nowhere. If we follow it further down here, we get the same thing. It goes through this coil, work its way through the switch, and show up here again. Kind of a dead end. So no current flow in here. Or maybe you could think of it this way. The only current that flows is a charging current to vary the pressure on this side to match the pressure on this side. So if you raised this to, let's say, minus 10 volts, then some charge is going to flow through here until this side gets to 10 volts, and then it's going to stop. And that's going to happen pretty quick, very quick. So here is the capacitor I'm interested in, the 0.02 capacitor here. On the diagram, it's not shown in a very obvious location for what it's doing. But you see it's connected between the AVC on the far side of the big resistor, and the other side is connected to the B minus here. So this guy's job is to dampen the variations that can occur on this side and drain out any RF that's made it through, because there could still be RF. This is the, oops, not that one, yeah, this guy. I got quiet suddenly. So exactly how they are dealing with the RF here seems odd to me, that this would be fed through to here, but there's a route back to the B minus. This is a large capacitor compared to this. So I think this is basically a connection to B minus here. So the job of this capacitor is to get rid of the RF that exists in this rectified line here. Oh, I'm not talking very well today. Okay, maybe I'm talking too much. So what happens if this capacitor is not so good? If it has no capacity, then you would get variations in the voltage on this side that would follow very precisely the variations over here. You're dealing with the grids over here and the output from those tubes. You have basically an oscillator feedback system set up. So I think without this capacitor, you might get some weird feedback things going on. What if this capacitor were shorted? Well, that would drive out the bias on these two tubes. You'd have no AVC action, and what you would really end up with? I think you'd end up with a silent radio. I think it would silence it. Okay, but what if this isn't the right value of capacitance anymore? Like, what if instead of 0.02 it's 0.01? Well, that wouldn't make much difference. But if this has fallen off, maybe the lead broke on this capacitor, just pretending, okay? The lead breaks right inside the capacitor. You still have some capacitance, so it just become very, very, very small. And AVC voltage here would no longer be controlled or dampened. And again, you might get some oscillations or some weird behavior in the radio of that sort. So let's find this capacitor we'll test it and see how leaky it is. I should really test you know what I should do? I should feed in a signal into the radio, tune that signal and measure the AVC voltage that's resulting from it, and then change this capacitor and see what happens. See if any change occurs. That sounds like the way to do it. So first thing is set up a signal generator. Boy, I've talked a lot and I haven't done anything yet. Let's okay, good. What? What? You know what it is? I drank a lot of coffee already. Maybe that's coffee overload. Okay, let's locate the AVC capacitor. So this is the first tube. This is the IF amplifier tube. This is the detector tube. This is the second IF, a little hole here where the wires are coming out. So there's something quite obvious about this resistor sitting right here, mounted dead center and up on a terminal strip. And look, there is a capacitor connected to it, kind of hidden right there. One end of it is going to this terminal. This terminal is pin number 8 on this tube, and I can tell easily because pin number 1 is soldered to the chassis there. So that's 1. This has to be 8. 8 is the cathode, and the cathode is on B minus. So here we've got a capacitor connected to B minus. This resistor is connected to a black wire which is going down to the IF transformer. So there's another wire coming up here, and it's connecting to these two terminals which are bridged. There's a wire between them. These are the two diodes, and they've just been shorted together to work as one big diode, one bigger diode. So this is the rectification of the output of that IF transformer. The other end of the secondary side of the transformer is here. This has got to be the case because there's another wire running right up to the input side of the volume control, which is carrying the audio. So at this point here, we've got both the audio signal as rectified by the diodes, and we also have that AVC voltage. Here's a resistor. Is this resistor 11 megohms? Now it's, body and dot, I can't tell. I can't tell. So we're going to make a reading. Okay. Secretly I did this off camera actually, so I actually know. No, let's check it out. Here we go. So see, it's headed for 11 megohms. So, I mean, this is a whopper of a resistor. There's nothing else like it in this radio. This has to be, for many reasons, that has to be the resistor. So we have the low impedance side, the high impedance side, and the high impedance side is a capacitor tied to B minus. This has to be the capacitor I'm after. Okay. Well, it sounds very reasonable. Very, very reasonable sounding. So I'm going to nip it off here. And we're going to nip it right out of here. Try not to cut the resistor with it. The resistor lead. Easy. 0.02, just as said on the schematic. Now, is this guy leaky at all? Well, yes. That would be my guess is yes, he's leaky. All the rest were. The question, I guess, kind of is, how leaky is it? Now, this is only a qualitative test I'm doing here. I can't tell you how many coulombs per minute leak through this, under a certain voltage. The voltage this capacitor is sustaining is very low, 10, 15 volts at the most. So it's not under a lot of stress inside. A capacitor like this that's got, say, 120 volts of alternating current across it, maybe it's right across the line, that guy's getting beat up much more than one like this. But let's see what's happened. So watching the eye, here we go. Well, that's one of the better capacitors for sure. It's opened almost all the way. So at 150 volts though, the leak is too much for my machine. The eye is not opening at all. So again, just how much of a leak? I don't know. You know, with this, is there enough of a leak in here to bleed down the charge that's built up in the high impedance part of the AVC circuit? Gee, I don't know. I was supposed to do a test before I cut that out, you bozo. Once again, I've done it. Oh my gosh, what are we going to do now? I've cut the stupid thing out of there. Oh no, it's not stupid. The stupid is for me. That was dumb. That was dumb. I'll blame it on my cats. I went outside for a while on my deck. And cats, they threw me off. Well, it'd be silly to try to reinstall this and replicate the test. That's just dumb. How many times have I done this kind of thing? Many, many, many times. I get a good idea, but then I forget it. Okay. Well, we're still in a position to operate this radio with no capacitor there and find out what happens. Yeah, I can do that. Okay, let's do that. What now? What could happen? Well, something really bad? Could something really bad happen here? No, I don't think so. Once again, it's just my reputation that's at stake, and it's already so beat up. What does it matter? Okay, here we go. Okay, power on. I think the radio's going to howl and shriek and go boop, 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 and do all kinds of weird stuff. We will see. And it could be very dependent on the position of the volume control. Are we on here? We're on 116 volts. We are on. Well, that sounds pretty normal. Now that has a bit of a garbly sound to it. There's a swooshing as I tune. Shoo, shoo. Let's get a station here. No stations. Not receiving a thing. It's an interesting sound there. That sounds like an open circuited grid. Oh. Also sounds like my hand is on the chassis. But it still has that open circuit grid sound to it. And that's kind of what's happened here. I've taken the capacitor off this high impedance circuit. There's nothing now holding it down, if I can put it that way. Plus the bias now would be, well, who knows what it is. I have to put a voltmeter on it. Yeah, I really blew the opportunity to do an interesting experiment here. But how come it's not picking anything up at all? I think it's going to start howling. Aha! She's a howler. So it's not mattering much at the bottom here. Except it's not picking anything up. Huh. Okay. That's a little surprising. It sounds like it's working fine, but it's not picking up any signals. Just because I took out the AVC capacitor. Let's put some equipment on this and fool around a little more. I sort of still have an opportunity to maybe learn something here. Okay, so we're going to use this meter. I've got it standing. You shouldn't probably have it standing up like this, but if I put it on its regular angle, you can't see a thing. So we're not doing precision measurements necessarily. It's on the 3-volt DC scale, and negative voltage will drive it upscale. And now I'm going to stick this on the high impedance side of the big 11 mega ohm resistor. So we're introducing some interference, that clicking interference, which I can't really hear now. Voltage is around 3 volts. 3 volts negative. Now if I tune the radio, just touching the chassis is doing that. Okay, hanging on tight to the chassis and tuning around. We're getting no AVC voltage action here. Up in the oscillating area. So I think it can be said, putting this meter on is affecting the circuit enough that whatever I'm measuring has to do with a state different than what we hear when the meter's not on. So don't really know for sure what I'm getting there. This is a very high impedance meter, about 10 mega ohms. But I have another one which is much higher. But maybe we will try that out. Now it could just be these leads, long leads being used here. I have this one clipped back to the B minus point, A B minus point. What about the other side of this resistor? So this would be on the detector side. Oh, that's pretty interesting. How does that happen? How do you get a lower voltage on the input side of the resistor than on the output side? Wow, that is interesting. Hear a hum come out of the speaker here. And it's probably the meter picking up hums and conveying it into the radio. I'm basically touching the input to the volume control. When I go on the other side of this gigantic resistor, you don't quite hear that, but look at all the other. What's going on here? How do you get that voltage there? So there is an effect called self-biasing. There can also be in some radios a base bias. So they set up a circuit to produce a certain bias on the tube, and then the AVC will drive it more negative if needed. Otherwise, with no AVC input, the bias will end up resolving itself at some set point, not zero. Not zero. Maybe. So maybe that's what's going on here. A self-biasing effect. These. The other thing too is the AVC is fed to 2 grids, 2 tubes. And without that capacitor, there's no decoupling between them. So I have the first 2 grids basically connected together. Am I getting this right? So there's a wire coming off the high impedance side of the big resistor, disappearing in a hole, and I'm pretty sure that's heading for a grid cap. Let's just see. I I can't bring myself to pick a radio up with the power on. Okay, we'll flip it over and we'll take a look. So yeah, you know what? It's going, no, it's going to the antenna. What? That's right. It goes to the antenna because it goes through the antenna winding to get to the first grid. So that's what this. So this yellow one here, the power's off now. This yellow one is going to tube number 1. Now we got another wire coming off. It's coming over to this transformer or coil. How does that fit in? It doesn't go anywhere. It must go through this coil. So this is the coil the AVC goes through to get to the first tube. This is the antenna coil. Then, yeah. Boy, this is a bad day for me when it comes to thinking about this stuff. Oh, what's going on here? We are off, yes. Well, I can, you know what we can try here? I can put a capacitor decade box in here, and we can fool around with various sizes of capacitor and see what see what nonsense occurs from that. Now that means a lot of wires going out to the decade box. And do I have? So I have one decade box just sitting right here, and it'll go from 0.0001 microfarads all the way up to 20. Let's try this guy. This is the Olsen resistance and capacitance multi-substitution box. Okay, Mr. Olsen. That radio's off, so I'm just going to clip this where that capacitor was. So one lead was on B minus. I can pick it off down here. Ooh, just an awful lot of wire. And the other lead would go on here. Oh, let's just check the settings there, Jim, before you do that. So we're going to want to use the capacitor only setting to start with anyway. And we have capacitor half, 1, or double. We're going to go to 1. And external, internal, what is that? External. So we'll leave it on internal. I think we must maybe, I don't know. Offhand. I think this is good. And we're going to want not to have this up at 20 microfarad. We'll start with 0.01. And I'll be able to connect and disconnect to this nice terminal right here. And we can witness the effect of this. Let me just put this in a little bit of a safer spot. There. Okay. Now, just having this piece of equipment connected may be enough to throw everything crazy. You have to turn the radio back on. Give it some time. If you think about it really hard, the only thing we have of value in our lives is time. Okay. The radio is tuned in an area. It should be picking up stations. No stations. Okay, so we're going to hook up 0.01 capacitor, supposedly. I don't know how accurate this box is. Not necessarily accurate at all. Seems to be receiving a lot better, but what's it receiving now? Could be, could be receiving from the box. The box could be the antenna. Let's see if we can get a station. Oh. Well, that sounds pretty much like the radio did sound. Of course, the capacitors in here can be leaky. I don't think I've changed these out to make them like new. What happens if we double the capacitance? Nothing. Did we really double it? By I don't know for sure. What if we go up by a factor of 10? How about a factor of 50? How about down? 1/10. Half of 1/10. What if we assume that setting this to 1 is not working right? So 0.0001, 001, 01, 0.1, 0.5. So the winner is 0.001. If we snap this, okay, that's the setting. We're going to take it off. I'm surprised this worked at all. Don't know why not having a capacitor there necessarily is killing it. That's something interesting to look at. I'm going to measure the capacitance here. Again, how valid is this measurement? So this was the winner. This was the best setting on here. What do you tell us? So it tells us it's a 0.01, a bit of a loss in the capacitor, but I don't think that's important. 0.01, 11 nanofarads, 0.01, and you know what? That's really what I got it dialed to, 0.01. Except I have the half setter. Let's put this up on 2. Just do an experiment and see if this. Oh, okay, it's decided it's a resistor now. Right there. Looks like I gotta spend some time on this box. Another resistor. Capacitor, same reading. So something's wrong with the box here. Maybe a couple settings that aren't really working right. But with it set to a half, turns out this 0.01, hey, turns out 0.02 is a good size, I would say. Okay. Not really sure what I'm learning here. Getting results that don't kind of fit with what I would expect. That tells me I got gaps in my knowledge. Hey, no surprise in that. Okay, I'm going to put in a 0.02 capacitor, and what we'll call that. Well, we'll see what happens. That's what we'll do. So why without that capacitor would this radio not receive any stations? Yet it sounded like it was kind of working. This is the capacitor here. So you picture this removed completely. Well, wait a minute. Let's go the other way around. What is it doing? So this side is hooked up to B minus. So from a signal point of view, B minus is here, and or ground. Maybe I can use the term. Ground is here. It's grounding this line, signal-wise. It's allowing DC to be on it, but not allowing any signal to be on it. If you follow it across, you get to the bottom of this coil. Now, I noticed this earlier about this schematic. If you follow the line up, you find a dot here. I think that's a mistake. I think that dot shouldn't be there. It should look like this, just going across. Because if this coil is hooked up like this, there's nothing here. This coil is not here. So I have to think this is a mistake. So what's happening is you're providing a... Now I'm silent again. As you're trying to get a signal to this point to go to the grid. And what is the switch? What switch is this? What switch is this? Okay, just looking around. Oh, there is a switch. Oh no, not the switch. I forgot about the switch. Yes, there's a switch on the back. and you're switching. Oh my gosh, you're switching from taking the signal out of the antenna, which I believe is how it's connected, to taking the signal, I guess essentially from this wire through the transformer. So the transformer is not doing much when you're utilizing the loop antenna. And the AVC voltage path, assuming again this dot is wrong, up through here. Now, if you have this switch the other way, up here, so you're using the loop. Is there a note? Did they make a note here? Not really. What is this? What is this supposed to be? 330. 322. Q 322. Q 323. Q 324, 325. Q. Well, I don't know what that is. You know, when I come across stuff I'm doing these videos, I don't know what it is. I make a comment. Gee, I don't know what that is. I'm without saying it, I'm inviting others to make comments on the video to explain the thing I don't understand. So others who are watching this video can read the comments and learn more stuff, because my knowledge is only what it is. So I don't know what they're getting at here with this Q stuff. It just seems like a numbering system for what? This is a switch. This is a coil. Well, you got two arrows here. There's a Q here. No arrows. No arrows. I think they're just making sure you realize this is Q. Yeah, not getting it. Seems like I don't know. Okay, never mind. So what's going on here? So once again, right now the radio's showing switch to the external antenna. So we throw the switch up here. We're now using the loop antenna, which has a Q number. And this would be okay, because you're not using this at all. I don't get what they're doing in here. So the AVC voltage is gonna potentially follow this line, then travel through the loop antenna. I saw the wire heading up there, and come out to here, where the switch would engage it, and then the signal would head to the grid from there. I better make sure that I better look at that switch. I'm gonna look at that switch right now because I think it's labeled, and the switch is set to loop. Luckily, okay, set to loop. Set to loop. That's what I thought, because I encountered this earlier. I've just forgotten about it. Well, what? Well, okay, I was trying to figure out why wouldn't this radio work at all with this capacitor missing, and I was kind of going down the road that it's providing a ground to, well, here. So you're providing a ground on this end of the loop. The other end of the loop is tied to the grid. That kind of makes sense. But if you don't have this capacitor, then the only way to ground is through this guy and through a bunch of stuff, and maybe you never make it there really. So this guy's purpose maybe not so much to dampen the AVC, maybe more to provide a signal ground on this side to make this antenna work. And without the ground, the antenna doesn't work well. It's not got it can't supply the juice. That's what I would have to conclude. So that's why when we put this in, suddenly the radio starts working again. Okay, as I said before, everything with a grain of salt that comes out of my mouth, because maybe there's probably more to the story here than I'm even picking up on. Very good. I have found, working on these radios, that the way this is done, the way the chassis is grounded in, other aspects vary a lot from radio to radio, and there's subtleties in these circuits. Too subtle for me. Let's play the radio now and see what we got. I'm really not trying to explain anything to anybody but myself, and you're along for the ride. That's kind of how this is really working. And I'm the kind of person I love to discover. I love the hands-on discovery thing. That's what I'm trying to, it's one of the things I'm trying to enable here. Have the experience of discovery. Yeah, sometimes all I'm discovering is my own mistakes, but nevertheless. Okay. Let's play this radio again. Let's see what we get out of it. Here we go. So I got no meter connected, nothing connected. The radio is by its lonesome here. This is your chance to shine, Mr. Radio. Well, radios don't shine. This one doesn't even have a light bulb.
It also makes it much more difficult to even qualify for the Olympics. After such optimism, looking at
well, I think that's improved.
Players, Jorge Fernandez, new head coach, all of what he's had to battle through. Dominant the first 3 games and came up with a bit of a clunker against Brazil. Blowing that 12-point lead in the third quarter definitely was a missed opportunity. We'll see if they can bounce back. That's tomorrow morning at 9:30 as they take on Spain. Later in the show, we'll talk some NFL.
This effect is gone.
Coming up at the top of the hour, and Alex.
I think I tuned it.
Rejoins us. Alex, we were just talking again about Spain, and their disappointing loss velocity is equal to the disappointing loss Canada had against Brazil. Yeah, no,
Looking for other stations. This is 590.
Will the Spanish team win against Canada? Essentially,
640 is not there. Oh. I think that's 640. $680. Very good. Where'd he go? Well, they're all coming from Toronto. There's the French station. Well, it strikes me that changing that capacitor has improved the reception of the radio, improved its performance significantly. I think I've gone from getting 1 station or 1.5 stations to getting 3 or 4 now, and this is just about as good as it gets in my shop here for a radio like this. So that actually turned out to be quite interesting and unexpected, and I think it has to do with what I was saying, that this capacitor's job may be more than one thing. It may be doing the AVC dampening and at the same time providing a ground to the antenna system, a signal ground back to B-. Okay, that's it for today. Time for me to go outside. I think I've got a lawn to cut. I got lots of stuff to do. So, well, thanks a lot for watching. Sorry I talked too much in this particular video. and probably half of what I said isn't particularly true either. So, but thanks a lot for watching, and tomorrow we'll pick another capacitor and try to tell the story of that capacitor. Try. See ya.